Good morning, Calc fans. How we doing this fine morning? It's Thursday morning. It's sunny outside right now. It's sort of nice out, so you should get outside and get some fresh air. Hope everybody's doing well in your household and your family. Hope everything's going well for you. Once again, if you've not completed any of or if you have not completed the quiz, please make sure you get that taken care of and get that picture taken to me as quickly as possible. Today what we're going to do is we're going to continue on with definite integrals, the idea of definite integrals. What we've done up till now is we have given approximations to these definite integrals by doing the upper sum, the lower sum, the Riemann sum. We've given approximations, but we haven't found an exact value. Well, the idea of integration will allow us to be able to determine and calculate this exact value, and that's one of the biggest applications of integrals outside of doing antiderivatives and undoing functions. The definite integral allows us to be able to calculate the actual area between the curve and the x-axis over a specific interval. Definite integral is find the area between the curve and the x-axis from -1 to 3 of the function x squared plus 1. Okay, that was the problem we dealt with initially with the upper sum, lower sum, and so on. With the idea of definite integrals, we dealt with the indefinite integrals already, which was more the idea of taking the antiderivative, undoing the idea of derivatives. That gave us the antiderivative. That was an indefinite integral. The definite integral allows the calculations, the area between the graph of a function and the x-axis over a particular interval. And that's basically what we are estimating here. We had this function, we had this interval, and we are approximating this value. And this is what we will be utilizing, this process here that we're going to go through here, this is what we'll be using to finish out the rest of the school year in calculus. Once again, we have the antiderivative stretched out s, taking the s and stretching it out. We have a lower sum, which is a value that's going to be here. We have an upper sum, that's going to be a value that's here, or upper limit. So we have a lower limit and upper limit. Well, when we're talking about the interval, x is a member of -1 to 3. This is your lower limit at -1. So this will be the lower limit. And the value of 3 will be your upper limit. We have the variable of integration, and then we have what is called the integrand. This integrand basically is what we are taking the integral of. So it'd be your f of x is equal to x squared plus 1 in this case. We want to let f, capital F of x, be the antiderivative of lower f of x. We'll still be doing the antiderivative idea, but the capital F of x is the antiderivative for lower f of x. Now, what we have to make sure of is what we're not going to do is we're not going to add in the plus c now. But if I take the antiderivative from a to b. So we're looking at a function x, and we're looking at limits of integration from a to b. If I take my antiderivative of my function and evaluate it at b and subtract off the antiderivative evaluated at a, this will give me the definite integral. This will give me a value. So it's a value of an integral. So if we're taking a function, we have a function f of x, we have an interval from a to b, we take the antiderivative, evaluate it at b, which is your top value, and subtract off the antiderivative evaluated at a. Now we have to remember our antiderivative rule. If you remember our antiderivative rule, we have ax at the end, dx, and this is just a review for this. How we take the antiderivative, we add 1 to our exponent and divide our coefficients by n plus 1. Now, how this is written, once again, if I have from A to B, how this is typically written in is we put a line there and tells us that we have to evaluate this at A and evaluate it at B. Now this A is a different value than that. It is a constant. It's a different value from that value. So if we take a look, this is the problem that we've been working on with all the estimations and approximations. We have x squared plus 1. And we want to take the definite integral from -1 to 3. So we have to use our exponent rule over here. So we're going to get an x cubed, because we have to add 1 here. And we divide our coefficient of 1 by our new exponent. So we have 1/3 x cubed. And then remember when we had a constant, we just have an x in there. And we want to evaluate this from -1 to 3. So what this is here, the capital F is our antiderivative, which is what we just calculated here. Our A and B is our limits of integration that we're dealing with here. So we need to evaluate our antiderivative at 3 and subtract off the antiderivative at -1. So if we evaluate this at 3, this is 3 cubed divided by 3, we have a value of 9. This is 27 divided by 3, plus the value of 3. This is my evaluation of the antiderivative at 3. I get 3 cubed, 27 divided by 3, which is 9, plus 3 times 1, which is a value of 3. And then we have to subtract off my value of evaluation at -1. So I have -1 cubed, which is -1. So we have a -1/3 there. And then 1 times -1, which is a -1. You really have to watch your negative signs here. You have to watch your negative signs, what's going on with the negative signs. So we get a value of 12 minus, this gives me -1 1/3. We have minus a negative, which turns into 12 plus 1 1/3. And the actual value for my area is a value of 13 1/3. Which, if you remember back, we started out between 9 and 19, and then it continued to squeeze down by the squeezing theorem. Those boundary values from the left and right sum, or upper sum and lower sum, continue to get closer and closer together. And then if you remember your trapezoid sum, our trapezoid sum came down to, I think it was 13.5. 13.5 was our trapezoid sum, which is a pretty good approximation, and we were close to that with respect to our midpoint sum too. So 13 1/3 is the actual value, and you can see even with our delta x being 1, the trapezoid sum and the midpoint sum was not a bad approximation to this. Was not bad, but the actual value is 13 1/3 squares. So if we take a look at another value problem here, the first thing we're going to want to do is take your antiderivative. Okay, so go ahead and take your antiderivative of x squared plus 2x plus 1. Good, take your antiderivative. So we have 1/3 x cubed, adding 1 here, adding 1 here, 1/3 x cubed plus, let's see, this will give us an x squared, and then we have 2 divided by 2, and then we have a plus x. And we have to evaluate from 0 to 5. Okay, and we want to put, once again, our limits of integration at the very end here. Tells us what we have to evaluate. So we first evaluated a value of 5. So we have 1/3 5 cubed plus 1 times 5 squared plus 5 minus, well, it's really nice when one of my limits of integration is 0, because when I integrate, I will always get an x variable in there. When I integrate, I'll get an x variable, which means when I put in the value of 0, I get 1/3 times 0 plus 1 times 0 plus 0. So we get a value of 0 at the end. So we take a look here. We have 5 cubed, which is 125 thirds, plus 25 plus 5 minus a value of 0. So now we just have to evaluate. We have 30, 125 thirds plus 30. So if I find this value, this comes down to, oh, this is 41 2/3 plus 30. If I take 125 over 3, it goes in 4 times, goes in once with 2 left over. So we get 71 2/3 squares. Find the area bounded by the graph of the function and the x-axis over the interval from 0 to 6. So if I take a look at my graph here, this is going to be my graph. And we want to calculate this entire area from 0 to the value of 6. Okay, so I want to be able to evaluate from 0 to 6. Now if you remember back, I want to find my total area here. So I cannot just sit here and take the antiderivative from 0 to 6 of x squared minus 4 dx. Because if I do that, the problem we run into is, if you remember back, this area was negative and this area was positive. So if I just calculated my antiderivative, what's going to happen is these two areas are going to cancel out. So what we need to do is we need to break this down into 2 different integrals. So we can take the integral from 0 to 2 of x squared minus 4 dx and add it to the area from 2 to 6 of x squared minus 4 dx. Well, you might sit there and say, well, this is still going to give me a negative area. Yeah, so what we need to do is just take the absolute value of this. So, taking a look at our antiderivative, we have 1/3 x cubed minus 4x from 0 to 2. And once again, we need to take the absolute value of this plus the exact same antiderivative, 1/3 x cubed minus 4x from 2 to 6. So what we have to do is we have to separate into 2 antiderivatives. which we're able to do. We're just looking at this one and this one separately. We're looking at, this is what we can do. So if we evaluate at the value of 2 first, we have 8/3 minus 8. Oopsie. This is my evaluation at 2, and then we have to subtract off our evaluation at 0. Well, once again, the nice thing about the zeros in here is I get 0 minus 0, so I have a 0 in there. So if we take a look, we have 8/3 minus 8, so we have negative 5 1/3. Because this is be 2 2/3. So this is going to be negative 5 1/3. So you can see this area here is going to give us a negative area. That's why we have to take the absolute value of it. Then we come over here and we have to evaluate at 6 minus the evaluation of my antiderivative at 2. So we have 1/3 times 36. So 36 divided by 3 is 12 minus 24. This should just be a parenthesis. We have 12 minus 24 is my first value. Because I evaluated 6. Let's see, 36 divided by that minus 24. We're good. And then we subtract off my evaluation at 2. So if I subtract off my evaluation at 2, I get a value of, let's see, this give me 8/3, I'm sorry, 4/3. This should be a cubed. There we go. Sorry about that. So we have a value of 8/3 here minus a value of 8 here. And that's my valuation at the value of 2. So if we take a look, we have negative 12 here. And this still gives me my negative 5/3, or 5 1/3. Now, I made a boo-boo here with this value. So I take 6 cubed. I was wondering why that's had a problem. 6 cubed divided by 3, 6 cubed divided by 3. All right, that looks a little bit better. It gives me a value of 72. That's a little bit better. So I have 72 minus 24. So we have 48. 48 minus 5 1/3. Okay, so once again we have to watch minus a negative. That gives me a positive. So we have a plus 53 1/3. So adding these together, we come down to 58 2/3 squares. Once again, when we have an area that's positive and negative, we have to be able to separate into 2 different integrals. Okay, this will be the last of the new material for this week. I have a worksheet for you that I posted online. You can work on that tomorrow also. It gives you some practice in calculating your definite integrals. I have nothing else new for you tomorrow. Just complete what we have here. Once again, the basis of this right here, we will be utilizing the rest of the semester. Okay, so we have probably maybe about 3 weeks worth of new material here, 2 to 3 weeks worth of new material that we will be able to get through sometime in the beginning, second week of May. We should be done with everything we need to get through. And then we'll prep for a final, and we'll have a final over this material. Other than that, once again, please continue to keep up with the work University of Findlay is requiring for your college credit. You need to continue to work, continue with the work that we have here. So you need to continue to work forward and continue to push yourself forward. Once again, if you have any questions, feel free to ask me, comment me. I'll get back to you as soon as I can get back to you. Other than that, keep up with the work. You folks have a great weekend. Adios.